Welcome to today's webinar. The topic today is calculation of aluminum all-glass railing. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Sonja von Bloh will be the presenter. She is, for example, responsible for the standalone program RSECTION and the add-on aluminum design, and she works also in the customer support team. Okay, then I say something how you can ask questions, at least for the attendees who participate the first time. First, I switch off my webcam that you can see the full screen. You can use the webinar control panel desktop, press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. And you can also adjust audio settings. If you hear us too loud or not, or we are too quiet. Okay, then the other possibility is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Sonja. Sonja, you can start.
Thank you for the introductory words. A warm welcome from my side as well to today's webinar. I'm pleased to present to you today the structural analysis of a glass aluminum railing. The focus is on an aluminum base profile. This profile is anchored to a supporting surface with screws. The glass panel is fixed in place using clamps within the base profile. Step by step, I will demonstrate how to model the system in RSECTION and Rfem and how to design it using the aluminum design network. I'll compare two different modeling approaches, one using members and the other using surfaces. The goal is not only to show you how the software works, but also to highlight how the modeling approach influences the structural behavior and ultimately the design results. Cross-sections in RSECTION can be created in various ways, via graphical or tabular input, by importing a DXF file, using a script or the API. In this webinar, I will show how to create a cross-section using a DXF file. To do so, I open the import dialog via import DXF, and then I choose the corresponding DXF file. 3 import methods are available with the create DXF template for further editing. The lines in the DXF file are imported as simple lines. These can be used as modeling aids. The other import options automatically generate elements. These are required for section classification, effective cross-section calculation, and thin wall analysis. They are also necessary if the section will later be converted to a surface model in Rfem, as only elements are converted into surfaces. The surface thickness corresponds to the element thickness. I choose the Create DXF template for further editing option and then assign a material from the library. So I open the material library, and then I look for an AW1663. This is already chosen here, so I click on OK, and then the necessary lines will be created. In the base data, I select the analysis method. Two options are available: the finite element analysis and the thin word analysis. I opt for finite element analysis. Next, I create the part which is required for all analysis methods in our section. Using the select boundary function, I select an outer contour of the cross-section, and then the part is generated automatically. I then define an opening using also the select boundary function, and then I click on the corresponding lines to create the openings. To improve clarity, I hide the parts and the openings in the display navigator. Next, I create elements. This is necessary for cross-section classification and to use the conversion to surfaces. Since the section is symmetrical about the z-axis, I model only half of it and create the other half using mirror. I generate elements with the function create center elements between parallel lines. Only two parallel lines need to be selected, and then the element is created automatically. Its thickness is derived from the spacing between the lines. I will do this for all elements now. Afterwards, I extend the horizontal and vertical elements on both sides. For this, I select first the horizontal elements and then the vertical elements, and I use now this function to next line or element. Here I extend both element sides. I do the same for the diagonal elements. So I select first the elements which I want to extend. And then I choose again this function to next line or element, and I modify both elements sides. Since I only want to model half the profile, I shorten the horizontal elements. I mean here these elements, by setting the y coordinate of the 2 points that you see here to the 0 point. The elements are not yet connected. To do this, I use the connected lines and elements function, and I select the entire cross-section using a selection window. I delete 2 redundant elements, here this element and this. Then I select all elements and choose now the mirror function. I want to create a copy. Mirroring axis is the z-axis and the point is the 0 point. Now the cross-section is complete, so I can save this cross-section. And then I move on to modeling the railing in Rfem. First, I show the creation of the base profile as a member with a glass pane rigidly attached. I create a new model via File, New, and I name this model Member Model. I select the type of model 3D. I then import the aluminum profile via New Cross-Section. I open here the cross-section library from RSECTION, and then I choose here the base profile. The material defined in RSECTION is retained. I set the work plane to XZ and enable the view a negative Y direction to simplify modeling. The member is created using this function single general. Here I choose this RSECTION, cross-section, and I use the import mode, length and direction. Here I define an angle and work plane of 90 degrees and a member length of 1200 millimeter. Now I create the glass panel. I select the member line and use then this function move copy. Here I want to create a copy. I define a displacement vector in negative z direction about 900 millimeter, and then I activate the step links option and link lines with surfaces to automatically create the surface. For the glass surface, I create a new material, or I have already created it. It's a material thermally toughened float glass with a thickness of 21.5 millimeter. Then I click here on OK, and the glass is created. With the glass design add-on, it would be possible to define the detailed layer structure of the glass. However, since this webinar focuses only on the aluminum-based profile design, I skip this step. At the location where the base profile is anchored to the floor, I create nodes. For this, I open the Edit Member dialog and I use the option Nodes on Member to place nodes without splitting the member. The first screw is placed 100 millimeter from the start. 5 more screws follow at 200 millimeter intervals. I define the node distances in the tab Nodes on Member, and I use the definition type string. Then I switch here to absolute distance, and now I enter 100 space 5 multiplied by 200. First the initial distance, then 5 repetitions of 200 millimeters. I assign now on these nodes the supports. For this purpose, I select first the nodes and then I assign nodal supports. Here I create a new nodal support. I don't need these nodal supports, so I delete them. Then I adjust the FE mesh in the mesh settings. And I want to define a target length of 50 millimeter. Next, I define the loads. The load case self-weight is already created as a load case. The checkbox active self-weight is enabled so that the self-weight is generated automatically. I create a new load case named transom loads for the transom loads. And I assign a load category imposed loads. In this load case, I define a line load. In load direction Y and with a load magnitude of 1 kilonewton per meter. And I apply this load to the top edge of the glass panel. Only ultimate limit state checks are performed. So I open here the design situations. I delete all serviceability limit state design situations. because I only want to do ultimate limit state designs. The railing and loads are now fully defined. Next, I activate the aluminum design add-on in the base data. In the ultimate limit state configuration, I deactivate the stability designs because I only want to do cross-section checks. Then I switch to the aluminum design tables. I only want to design member number 1. Now I start the calculation. The results show a very low utilization of the profile. This is expected as the member model can only represent idealized loading. Local effects like point loads from clamps pressing on the web of the cross-section are not captured and therefore not included in the design. To consider such effects, a more detailed surface or solid model is required. Now I want to show you how such a surface model is built. So I save this file and I use the previously created member model and save it as surface model. I then convert the member into surfaces using the function generate surfaces from members. The elements defined in our section are automatically converted into surfaces with the corresponding thicknesses. I open such a surface here, and you see that the thickness of the surface corresponds to the thickness of the element. I round node coordinates now to 2 decimal places to eliminate inaccuracies. Next, I move the glass panel to its real installation position using the move function. Here I define the displacement vector by picking these nodes. The displacement should only be in Z direction. In the 2 bottom surfaces that I now select, I create openings for the screws. As the openings span multiple surfaces, I merge them into single surfaces by deleting unnecessary ones and redefining the surface boundaries. So I delete now the unnecessary surfaces and then I modify the surface. Here I choose the boundary lines of the whole surface. Same for the bottom surface. The center of the first screw hole is located 100 millimeter from the beginning of the base profile. The screw holes are spaced at intervals of 200 millimeter. To create the center points of the first hole, I copy these center nodes in X direction with a displacement vector of 100 millimeter. Then I activate the work plane XY, and now I create the openings on the lower surface. The openings have a radius of 7.5 millimeter, and on the top surface they have a radius of 14 millimeter. The diagonal plates also require openings at these positions. I define boundary lines for them. So I create now the boundary lines for the openings. I then copy these lines and also the openings 5 times in X direction with a displacement vector of 200 millimeter. Then I split the diagonal plates. To do this, I first select the diagonal plates, and then I use the function divide surface with intersecting lines. Then all I have to do is to remove the openings. In the next step, I define the contact between glass and my clamps. The glass pane is fixed at the top and bottom edges using clamps. Here on this top edge and this bottom edge. The contact between the glass pane and the base profile is modeled using surface contact. For this purpose, the relevant surfaces are divided according to the spacing of the clamps. Each clamp is 80 millimeter wide and positioned 80 millimeter from the start of the base profile. The distance between the clamps is 160 millimeter. To model this, I copy the 4 edge lines 14 times in x direction with a displacement vector of 80 millimeter. I then divide the surfaces along all intersecting lines. For this purpose, I first select the surfaces and then I use the function divide surface with intersecting lines. Between the positions of the clamps and the glass pane, I define a surface contact that is only active in compression. That is when the pane is in contact with the profile. Frictional contact is also taken into account. To do this, I first define a visibility. I select the corresponding surfaces and then I define the surface contact. In group 1, I choose all the surfaces where the clamps are located because we have only a contact between clamp or a contact at the clamp position between glass and my webs of my base profile. Surface number 2 is my glass pane. Then I have to define the surface contact. Contact perpendicular to surfaces fails under tension. Then I want to consider also a contact parallel to surfaces with a little shear stiffness. I have to define this on the other side too. So I create a new surface contact. Then I choose the corresponding surfaces where the clamps are located. And then the glass pane. At the clamp positions, the glass pane can bear on the base profile. These contact conditions are modeled using rigid links between the lower edge of the glass pane and the surface of the base profile. In some cases, screw holes are located within the contact zones of the base profile surface. Since rigid links can only be defined where no openings exist, I split the line at the bottom edge of the glass pane in the areas of the openings. The rigid links are then only applied in the segments of the clamps that are outside the openings. I first divide the lower edge of the glass pane into 14 segments of 80 millimeter each. For this, I use the divide line function. I then copy the arcs of the first 2 and last 2 openings to the elevation of the lower glass edge. The other clamps are located outside the screw openings. For this purpose, I use a visibility, and here I choose the arcs of the first two openings and of the last two openings. Then I copy these arcs to the lower glass pane, and then I use the connect function to define the nodes on the intersecting points. I don't need the arcs anymore, so I delete them. Then I can create my rigid links. For this purpose, I define a visibility. And now I define the rigid links. You find them here in the special objects. I create a new rigid link. I want to define a rigid link line to a surface. Then I have to define a line hinge where I activate the hinge in UI. And here I want to use also a nonlinearity fixed if negative, since it's only possible that the glass pane bears on the surface if there is a tension force, then there is no contact between the base plate of the profile and the glass clamp. Then I pick the line and the surface. I will do the step and now the last clamp. The support provided by the screws is modeled at the openings using hinged line supports. I will do this afterwards. For this, I use also the visibility of the arcs. And here I create a hinged line support on these openings. The base profile itself rests on the substrate. This support is modeled using a surface support with failure and tension. That means the support becomes ineffective when the contact stress in the Z direction is negative. I will do this now. So I select the surfaces of the base plate, and then I assign surface support in Z direction with non-linearity failure if negative contact stress. Additionally, the edges of the base profile are supported by line supports, also with the condition failure if PZ is negative, so that these supports are also only active in compression. For this, I select here the two lines and create now a new line support with support condition non-linearity failure if negative PZ. Next, I define the FE mesh. I assign a surface mesh refinement to all surfaces of the base profile with a target element size of 4 millimeter. So I select all surfaces. Then I edit the surfaces, activate the mesh refinement, and assign a mesh refinement with a target length of 4 millimeter to all of these surfaces. In addition, I define a circular nodal mesh refinement at the center of the bottom opening. So at this point, so I edit this node, activate the mesh refinement, and define here a radius of 20 millimeter. Inner target FE length should be 1 millimeter and outer target FE length should be 2 millimeter. I then copy this mesh refinement via move copy function 5 times with displacement vector index of 200 millimeter. In the next step, I configure the aluminum design settings. For the design, I select on the table objects to design all surfaces of the base profile. No further settings are required. Since I already performed the calculation in advance, I now open the pre-calculated file. The deformation clearly reveals the upward bending of the floor profile. They also illustrate the lifting of the cross-section from the substrate and the restraint provided by the screws. So I will show you only the surface where we can see the deformation of the base plate. These effects cannot be captured with a simple member model. Then I switch to the design results. So the aluminum design. And here you can see that the design results also confirm that the surface model leads to significantly higher utilization of the base profile compared to the member model. Local stress concentrations occur particularly in the areas around the screw holes and in the lower web region. So I show you this now. These zones here have a greater material thickness. However, for the purpose of this calculation, I used a reduced thickness to obtain conservative results. It would therefore be advisable to model the component thickness in more detail in these areas in order to achieve more realistic design results. This concludes the key differences between the member and surface models. Thank you for your attention. I now hand back over to Andreas.
Thank you, Sonja, for your presentation. I have an additional hint for you. You can book our online courses. For example, the Rfem 6 course, that's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with Rfem 6. Then the Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. For more information and prices, just click at the buttons on the bottom here, or you can scan the QR codes. You can get the courses for free, one single course for free when you send us a customer project. And when we have published it, you get such a course for free. Just write us an email to info@dlubal.com. I will receive that email and I will answer you what I need for information. That's not too much, I promise. Okay, then just join the Dlubal community. You can ask questions there, for example. then other users or we will answer you. Then you can use the GeoZone tool, the cross-section properties. You can download 3D models from our website. Just explore all our free services. When you click that button here, or you can scan the QR code, then you will receive such a page with a good overview. You can also download the full trial version. That's valid for 90 days if you don't use Rfem 6 already. Then you can find more information on our website, dlubal.com. For example, you can reach the Mia AI assistant. She is available for you 24/7, all the day, all the night. And you can answer, or you can ask questions, and she will answer you with the information from our website. Also with a link where she had the information from. Okay, then thank you for your attention. Thanks to Sonja for the presentation. I hope we meet each other in a future webinar. See you then. Bye-bye.